Hello friends, welcome to my channel. Let's have a look at a newly appeared problem. Problem 2457. Minimum addition to make integer beautiful. In this video, we're going to share two solution formats. So the first one is very compact, just for solving the problem itself. And the second one is more verbose, aiming to understand the finer detail and for coding skills. First, I'll read through the statement, and then we will do the analysis, and finally we share the code and explain during the process. So first, the statement. So we are given two positive integers, n and target. An integer is considered beautiful if the sum of its digits is less than or equal to target. We are required to return the minimum non-negative integer x such that m plus x is beautiful. The input will be generated such that it's always possible to make m beautiful. So here are three examples. So the example 3 is very special. So n and target are the same, so the output is 0, which is for sure non-negative. And in the first example, so if we add 4 to 6, so 16, so we are going to get 20, right? So 20 has a digital sum, 2 plus 0, 0 equals 2. 2 is less than 6, so the minimal number is 4, and this is also the return. So in example 2, so if we add 3 to 7, so we're going to get 470. So the digital sum is 11, still greater than 6. Then we're going to add 3 in the digit 7 corresponding to the tens. So we're going to get 500 in total. So 500 has digital sum 5, which is less than 6. So the overall we add 3 in 7 and add 3 in another 7, but in tens. So we're going to return 3 plus 3 times 10, that is 33. So this example tells us that the digit position is going to be important for us. So actually the three examples are not generic enough because we need to also consider zeros. For example, we have 1/6 followed up with a number of zeros, right? So we need to consider the zeros which have implementations on the digital positions to add. So with that said, let's look at the constraints. First, the range of n. N is bounded above by 10 to the power 12. This is a large number, but it's the digits which actually gives us an upper bound estimate on the length of this digit in decimal. For example, it's less than or equal to 12 or 13, so if you like. So the target is bounded below by 1 and bounded above by 150, right? So the input will be generated such that it's always possible to make m beautiful. So this is a consistency assumption. So with that said, so we're ready to do the analysis. So here I'm going to share two solutions. So the first is a compact version, and the second is an expanded version for understanding the finer details. So the treatment actually is straightforward in some sense. So we're going to making the digits from right, so in other words the least significant, to left to be 0 by doing addition. So the thing to be noticed is that so the next least significant shall be increased by 1, so which can result 10, right? So here we want to give a generic walkthrough so that we can notice the finer details and some subtle points. So I'm going to use n equals 2098 and target is 2. So the corresponding array is 2098, right? So the digit sum is 19 at the very beginning. So if we initialize digit position is 0, right? We want to add from 8. So the result is 0. So we can add 2 to make the rightmost digit to be 0. And the effect is that we popping the last element from the corresponding array, right? And then we add 2 to it. So this will give us a 1 in the adding to the digit nan. But this will give us 2, 0, 10, which is not the expected thing, right? So because if we add 2, so we get to 2098, so we get 2100. So we shall get 210. So this actually can be obtained by doing division, then plus 1. For example, here 2098. So if we divide it by 10 and add 1, so we're going to get 210, right? So in this case, we're going to result a corresponding list 210, right? So this operation makes the result to be 0 plus this 0 is the original state plus 10 minus 8 because we want to make a 10 from 8. So times 10 to the power digit position. So the first digit position is 0, so we get 2 added. So now the digit sum is 3, right? Because 210 digit sum is 3, and still larger than 2. So we do the above operation again. We want to make the digit 1 being 0 by adding nan to the digit 1. But the digit position is 2 now, right? So because here originally we are adding at 8, so now we are adding next to the most significant 2, right? So that's the 1. So in this case, this 2 is obtained by incrementing the variable digit position each time when we do a pop operation. For example, we pop 0, right? So the position is digit position is tens, and then we pop 1, so this corresponds to hundreds, right? So here we want to notice that each time when we do a pop operation, we need to increment the digit position variable, right? So this way, so we increment it twice, and then the corresponding number is going to be because we add nan, so this is going to be 300, right? So here the result incremented by the original state is 2, and then we add hundreds at this 1 digit corresponding next to the least most significant 2. So we get 10 minus 1 times 10 to the power position. So now the position is 2, so we get actually what we added is 900, so we get 902. So in this case, the n becomes 3, right? So digit sum of 3 is still larger than 2. So we pop a 3 and increment the digit by digit position by 1. So now the digit position is 3, and then the result is 902 plus 10 minus 3 times 10 to the power 3. So this corresponding to 7,000, right? Plus 902, that is 7902. So now the n equals 3 and divided by 10 plus 1, that is 1. But this 1 is representing 10,000, right? Due to the digit position. So this 10,000 is the last position. So up to now, actually, we have already get the result by incrementing and computing the sum, that is 7,902. So however, if we know the final number 10,000, we can also compute the addition by the final state of this result minus its original state 2098. So we also get 7,902. So this observation also gives another code format, but the above process is the detail we want to share. So notice that in this paragraph, so when we pop our zeros, right, we do not do adding 1, we just need to increment the digit position by 1. So with that said, we can actually have method 2. So this is based on the observation here. So we can, for example, this example. So we have 123. The target is 2. So the final number will be 200, and the return it will be 200 minus 123. That is 77. So the procedure is the following, right? So for now, the digit sum is 6, larger than 2. So we do division, then plus 1, we get 12. Then we increment the digit position by 1, we get position is 1. And then 12 still have digit sum, that is 3, larger than 2. So then we do division by 10 plus 1, so we get 2. The position is increased by 1 again, so that is 2. So 2 is still, 2 is the one which is less than or equal to the target 2. So the final number will be 2 times 10 to the power position, that is 200. So then we can use this 200 minus 123, let's get 77. So here you can actually try this in 1230. So target is still 2. So in this case, we shall return 770, right? Hopefully you digest the logic here. So based on the above analysis, first I'm going to write a solution which is more compact, and then we're going to write according to a verbose version in the first generic case walkthrough. So actually the latter is more on coding, and the first is more on logic, right? So first I'm going to write a compact version. So this is actually very routine for now. So we are going to mimic record the digit position. Originally is 0, and then the original number is n, right? So let's use current as n. So actually we do not need to introduce this current, but for the variable naming, so I'm going to, and the interpretability, I'm going to introduce this variable. And then we're going to do something like this. Well, sum. So we're going to compute the digit sum of the current number. So we're going to first use a map. So map actually applies a function, let's call it int, to a iterable. So here the iterable will be the corresponding string for the current number. So for the current, so and then what we're going to do, so let's do this. So if this is larger than the target, what we're going to do is that we're going to do current equals current. So we're going to do integer division by 10. This corresponds to eliminate the least significant digit. Then we plus 1, right? So the corresponding digit position is incremented by 1 each time. So this way, once we exit this while loop, so we can actually know the final number, that is current. And then what we're going to do is to the current times the power, right? And then we subtract the original number. So what we are going to return is nothing but the current state, and then this current is representing this number, 10 to the power digit position, and then we minus the original number. So this will be the addition part. So this actually forms a solution. So if we do not introduce these two variables, actually the code can be shorter. So now let's look at the test. Yeah, it passes the test case for 1230. So now let's look at generic case. Yeah, it passes all the generic cases. So this is the one format of solution. It's more based on the mathematics or logic. So now let's write another solution which is more which puts more emphasis on the coding. So I'm going to name the first one as version 1. So now we are going to do the second one in a verbose way, or from scratch. So here, to do this, we need to know the corresponding digital list and digital sum. I'm going to write two hyperfunction to do this job. This is just for a personal preference. So I'm going to get the digit list and the digit sum. So this give to the input or argument is a integer. So then we can get a temp. So I'm going to get a map. So I'm going to use the same logic above. And then I'm going to make a list out of this map object temp. And then we're going to return temp and the sum of temp. So the sum of temp will be the digit sum, right? And the first temp will be the corresponding list. And then what we're going to do, we also need to return from the array to the number. So what we can do is do this, right? So actually we do not need this second one. Let's use this only, right? So next we're going to initialize a result variable. Here we are not going to use subtraction. We are going to use addition as in the walkthrough. And then first I'm going to get the corresponding list and the corresponding digit sum. That is get digits and sum. That is m, right? So from this one. And then the digit position is 0 at the very beginning. And then what we're going to do is while loop, while s is larger than target, right? If the digit sum is larger than the given target, what we're going to do is that we are going to check if we can make the least significant non-zero digit to be 0 in order to shrink the digit sum. So for this, actually we need another loop. So for sure here we can use array -1 because at this stage the array must be non-empty, right? So if the array the end element is corresponding to the least significant digit is 0, so we need to do pops. So we're going to do array pop, and then each pop, so we are going to shrink the number by 10, right? So the digit position is incremented by 1. So this is while loop. So after this while loop, as we exit, then the array -1 will be non-zero, right? So then this is the least significant digit for now. So array pop. So what we want to add to this list is 10 minus this list, right? So what the result should be incremented by 10 minus this list, then times 10 to the power position, right? So this is the this digit represents tens of powers. If position is 1, it represents tens. If position is 2, it represents hundreds. So after this, we need to do this division again. But here is non-zero digits is corresponding to make a 10 and then carry to the more significant ones. So we need to n plus 1, right? So this way we finished the main logic, and then afterwards, so we need to update the state of array and s, the digit sum. So now the digits array and digit sum is going to be get digits and sum. This n, right? So, but now we need to increment the position by 1. So for next round. So with that said, so we are going to return the results. So this actually is the same as the first solution, but so we write in the finer details. So now I guess it's a time to do a test. Yeah, this passes the example again. So now let's test this one. It should return 77. So let's do another test. So for 16, it should be returned 4, right? So let's look at the generic case. Yeah, it passes all the generic cases. So these are the two solution formats for this solution. The first one is a little bit compact, and the second one is more with more emphasis on the coding part. So with that said, I guess that's it for this video. Thank you.